So earlier in the year, we began talking about the motion of an object moving at a constant speed. And in this case, the forces on that object had to be balanced so that there was no change to the motion. We learned how forces produce accelerations. But when we were talking about accelerations, we were talking about speeding up and slowing down. If the net force, represented by this orange arrow, pointed with the motion, then the object sped up. But if the net force pointed against the motion, in this case left while the ball was moving to the right, then the object slowed down. But what happens if we want something to turn? What if we have a bowling ball that's moving in a line, but we want it to turn around, say, this little dot here? Well, let's take a look at what they do in this video. So notice how there's someone with kind of a mallet that is hitting the ball, and if you would, kind of imagine the direction of their force, it's actually always towards that little central circle. In order to get the ball to turn, a force had to be exerted perpendicular to the motion. And to keep it turning, to have it go in a circle, they had to somehow get that force to stay perpendicular no matter what. And that meant that the net force, as is shown in this picture, points toward the center of the circular path. That's how you obtain circular motion. Now, if that's the case, and it really is kept perpendicular to the motion, what we find is that the speed of the object doesn't change. It doesn't speed up or slow down. It's just the direction of the object's motion that changes. So this is a new type of motion called uniform circular motion, where an object moves along a circular path, but it does it in a very consistent way with a constant speed. So let's again kind of think back to what we know. Forces cause changes in motion. Acceleration means that velocity is changing. So if a force is causing an acceleration, it's causing a change in velocity. But what we're seeing here is not a change in speed, but a change in direction. Velocity includes both speed and direction. It's not just how fast, it's how fast and in what direction the object is moving. So when you focus on circular motion, it's not about pushing something with or against its motion. It's about pushing perpendicular to the motion, which keeps the speed constant and only changes the direction. Some key facts. If you're taking notes, you might want to jot these down. What we'll call the instantaneous velocity, the velocity at a particular moment, it's going to have a consistent value, but the direction is going to keep on changing. And it's always going to be tangent to the path, which means if you have a situation where suddenly the force disappears, the object will move in a straight line, and it'll move in a direction that is tangent to the circle at that particular moment. We'll call that instantaneous velocity either a linear velocity or sometimes a tangential velocity to help us remember that it actually is directed tangent to the circle. The force that causes this all to happen has to be directed toward the center. It has to be perpendicular to that velocity direction, which would be along the radius at that point. The word that means towards the center is centripetal. So the net force is sometimes called the centripetal force because it's a force that points towards the center of the circular path. Therefore, we also have an acceleration that also points in that direction. And this is the weird thing. So the acceleration doesn't actually match the direction of the motion or even against the motion. The acceleration points perpendicular to the motion towards the center. And so it also is called the centripetal acceleration. So a weird thing about acceleration is that when you are accelerating, when you're experiencing acceleration, you actually feel like you're being pushed in the opposite direction of the acceleration. For instance, if you're at a stop sign and you start to speed up suddenly from that stop sign, so your car accelerates forward, you are going to feel like you're pushed back. You feel the opposite of that change to your motion. You feel sort of the reluctance to change. If you then slam on the brakes, there would have to be a negative acceleration against your motion. But you will feel thrown forward. You'll feel the opposite of what that acceleration is. So if that's what we feel when we're moving in a straight line, we should also have similar feelings when we're moving along a curve. And sure enough, when a car turns to the left, like is shown in this picture, the people inside feel pushed to the right. They feel like they're getting thrown to the outside side of the car. And so that's something to keep in mind, is that we don't necessarily feel the right thing. The false feeling is actually given a name. It's called the centrifugal force, or the centrifugal acceleration sometimes, but usually force. And it's not a true force. It's a feeling that we get because of this sudden change to our motion. The true force is an inward force, a centripetal force with a T in there. That's the one that is necessary to cause us to curve in the direction that we're curving. Let's take a look at how we would calculate some of these things. So this is a nice simple diagram just showing the radius of whatever circular path we're on, or our object is on, and then also that instantaneous velocity, which again we'll sometimes call a linear velocity or a tangential velocity because it's tangent to the circle. Remember that we are studying situations where the object has a constant speed, okay? So a constant value of v, which means we should be able to just take a distance over a time. But these distances and times have a particular meaning in this case. We're going to define them in terms of two important parts to the motion. One is the radius of the circular path, measured in meters, and we're going to use that to determine the distance by thinking about circumference, by thinking about that dotted line that you see for the circle. And then we're also going to focus specifically on the time it takes the object to go just one time around. So not just any old time, but specifically the time to travel through one circumference. And that's called the period of the rotation. It's given a capital T because it's a very special time. And so when you see that in a formula, it's not just, again, any old value of time. It is specifically the time one time around the circle. So when you put that together for an object moving with constant speed around a circular path, the speed can be found by taking 2 pi r, that's the circumference formula, divided by the period. Again, capital T, not just T. To find the value of the centripetal acceleration, you might think, oh, okay, well, I know how to calculate acceleration. It's the change in velocity over the change in time. But that's not going to work in this case because our value of v is not changing. So there isn't a delta v. It would come out 0. So there's a different formula when we're dealing with centripetal acceleration, this inward acceleration of the object. And it is calculated by taking the speed squared and dividing by the radius. So the faster something is traveling, the more acceleration is needed. And the bigger the circle, the more gradual the motion, and so the acceleration is smaller. Both of these formulas are on your formula sheet, the two that are in yellow. It's been updated. Then we have the centripetal force, but it's not a new force. It's not like we've been talking about, tension, gravity, friction, like it's a brand new type of force. It's not that at all. It's just the sort of special name that's given to the net force, sigma F, when the net force happens to point inward. So it's called centripetal because of its direction, not because it's a particular type of force. It always points inward towards the center. To calculate this is not really a new formula. It's just really pulling together two ideas one that was just introduced, that the centripetal acceleration is v squared over r, and then an old idea that the net force is mass times acceleration. So to find the centripetal force, you just take the mass times the centripetal acceleration. By the way, I did not put this in a yellow box because it's not on the formula sheet. This is not like a brand new formula, really. It's just a combination of two other ones. You, of course, can have it in your notes, though. So if you're asked to state the centripetal force, you might be doing a calculation. Okay, it might be a problem where you're given the speed and the radius and the mass, or maybe you're figuring out the speed first and then using this sort of an idea. But if you're asked to state the centripetal force, it might also just be asking, what is producing the circular motion? What type of force is pushing inward that's causing something to go in a circle? So if we had something that was orbiting a planet, like a satellite, in that case, it's going to be a gravitational force that's pulling the object towards the planet. That's really going to be described in our next topic. If we had like a bucket full of water that someone was spinning around, this is actually kind of like a classic physics experiment. There's actually two different ways of thinking about it. There would be tension pulling on the bucket because there's this string that's pulling inward on it. But if we looked at the water itself, there's a surface, the bottom of the bucket, that's pushing on the water. And so the normal force would be our centripetal force. If a car is traveling around a curve, you might think, oh, well, it curves because someone turns the wheel. Well, that allows it to turn, but what you need is an inward force that actually is pushing or pulling it along that route. And that force actually turns out to be a frictional force. You can't turn along a curve without friction. You might have noticed that if you're driving at all on slick roads. And then in this last picture, we have a roller coaster. And so many amusement park rides actually use circular motion as the means by which some sort of acceleration is given to the passengers. Some sort of excitement is conveyed there. But for these people who are going upside down on a track, there's actually two forces that point inward. That would be sort of downward from the top. There would be a normal force of the seat pushing on their body. And then there would actually also be gravity. So both of those forces would be part of the net force or the centripetal force that causes circular motion. We'll focus on that one as a challenge topic later in the unit.